Okay, so this is an interesting problem set. It was posted to the College Board site after the revision to the 2020 for the 2020 administration here. So there's some hope that this gives us some indicator of expectation of what this exam would look like. They also flagged these as problems for additional practice in preparation for that administration. However, there is one component of one of these questions that is outside the scope, and it's the one that is on the Lagrange error bounding. So I want to point that out and say that for the most part, this is a good set. We've seen most of the pieces of this set before, but I also want to make you aware that there is at least one component here that is outside the scope. All right, so the stem in the problem number 5 that they posted, we've seen before. This is the differential equation. In that it asks us first to verify a second derivative. And you have to recognize that this is implicit. So you're going to play low d high minus high d low over low squared. Okay? So this takes some rearranging. This is going to be 2xy times -1 plus y squared over x minus y squared over x squared, which is -2xy plus 2y cubed minus y squared over x squared, which when we rearrange things gives me the 2y cubed minus y squared minus 2xy over x squared. So that's part A of the problem. All right, we're going to look at part B of the problem that now is asking for us to determine whether or not we have a relative min or max at 4. All right, so the first thing to recognize is that when x is 4, y is 2. And we have the first derivative, right? The first derivative tells us, so dy dx when x is 4 is going to be -1 plus, and remember when x is 4, y is 2, so this is going to be 2 squared over 4, so this is -1 plus 1, which is 0, which is the first condition of the second derivative test that we need. We have to have the first derivative is 0. And then in part A, we got the second derivative, so we just start plugging in, right? We plug in 4 for x and 2 for y. So in the second derivative here, we're going to get 2 times 2 cubed minus 2 squared minus 2 times 4 times 2 all over 4 squared. So that's 16 minus 4 minus 16 over 16, which is -1/4, which is less than 0. First derivative 0, second derivative negative, means that I have local maximum. All right, so let's move on to part C. Okay, so part C gives me another initial value. This initial value tells me when x is 1, y is 2, right? And then it asks for the second degree Taylor polynomial. Now, this question is actually legitimate for the 2020 assessment. So let's take a look at this. You have the second degree Taylor polynomial would be h of 1 plus h prime of 1 times x minus 1 plus h double prime of 1 over 2 times x minus 1, centered at 1, squared, right? Now, h prime of 1 is the derivative at 1, so that's going to be negative 1, and remember 1 goes to 2, so it's going to be 2 squared over 1, which is negative 1 plus 4, which is 3, so that's h prime of 1. H double prime of 1 is the second derivative when x is 1, so that's going to be 2 times 2 cubed minus 2 squared minus 2 times 1 times 2 all over 1 squared. So this is 16 minus 4 over 1, which is just 8. So plotting things in, when x is 1, y is 2, plus the first derivative times x minus 1, plus 8 divided by 2 is 4 times x minus 1 squared, and that is the second degree Taylor polynomial. Now, the part D of this problem is not legit for the 2020 administration. So we're going to do it, but Lagrange error bounding is definitely not on this administration. All right, so we're going to bind the error between the actual function at 1.1 and the estimate given by the second degree Taylor polynomial. All right, so we need the maximum when x is going from the center at 1 to 1.1, which is where we're doing the estimate, of the third degree of x, the third derivative of x, over 3 factorial times 1.1 minus 1 cubed. All right, they tell us in the problem that that has to be bound by 60. 3 factorial is 6. 1.1 minus 1 is 0.1 cubed. So this is 10 times 0.1 to the third, which is the same as 0.1 squared, which is 0.01, which is exactly what the problem has to say. Now, what I want to note is that I did this entire thing without ever touching a calculator. Now, your problems on the test will be calculator active, both of them. However, they're saying that the problems can be done without using a calculator. So I believe that this is kind of in the right ballpark, that they gave me one stem, a whole bunch of questions off of the stem. There are varied types of questions, and they could all be done without a calculator if you needed to. Now, we're going to see this also in the question 4 that they released, that it meets all those same criteria. So think about this as you're doing your test prep. All right, so the other problem that they released at this time frame was, I have it in the thing, is the College Board Practice 2. It's a problem number 4. But you'll see it's got this table, and we've actually seen this problem before too, but we'll work through it anyway, just to kind of give you an idea of how it works one more time. The first thing here is it's asking me for f of 6, given the table, and f of 0, and using a midpoint Riemann sum, right? So part A, we use the fact from fundamental theorem of calculus that we're 0 to 6 of f prime of x dx is going to be the same as f of 6 minus f of 0. All right, so this is the thing we're using the trapezoid or the midpoint Riemann sum to deal with. Each of the intervals here has an interval of 2. So this could look like 2 times, and the midpoint here is 3.5, plus 2 times, and the midpoint of the second one is 0.8, and 2 times the midpoint of the third one is 5.8. We don't know f of 6, but we do know f of 0 is 20, and that's minus. All right, see, so that's 7. That's 1.6. and this is 11.6. F of 6 minus 20. What do we got here? 7, 1.6, 11.6, so that's 7, 8. 8 and 11 is 19, plus 1.2 is 20.2. And then you add the 20 both sides and you get f of 6. These are all approximates, actually. F of 6 is approximately 40.2. All right, so again, a place where the calculator could help you, but not necessary to do the problem. This is what they're going to look for on this test, is like you're getting problems where the calculator is not going to be the deciding factor. All right, let's look at part B. Part B starts with the fact that 0 is less than or equal to f prime of x, which is less than or equal to 7 for all values, right? That's in the stem of the problem. All right, so integrate it all. Integrate from 0 to 6 of 0 dx is still going to be 0 to 6 of f prime of x dx is still going to be less than 0 to 6 of 7 dx. Okay, this is 0. This is f of 6 minus f of 2, or 0. And this is 6 times 7 is 42. 0 less than or equal to f of 6. This is 20. Add the 20 all around, and we get that f of 6 is bound between 20 and 62, which means that f of 6 cannot equal 70 because 70 is outside of 62. So there's part B. All right, so let's look at part C. Part C takes the integral from 2 to 4 of f double prime of x dx. Okay, so it's asking us what this is. Well, if you know the fundamental theorem of calculus, this is really just f prime of 4 minus f prime of 2. Read the table. This one's 1.7. That one's 2. You're at 0.3, negative 0.3, and you are done with the problem. That's all there is to it. If you recognize it as an fundamental theorem of calculus problem, it's literally just plug in values. All right, let's look at part D. All right, part D of this problem says I have the limit as x approaches 0 of f of x minus 20e to the x over 0.5 f of x minus 10. All right, so when you just plug these in, you're going to get this is f of 0 minus 20e to the 0 over 0.5 times f of 0 minus 10. You're told that f of 0 is 20, so this is going to be 20 minus 20e to the 0 is 1. Half of 20 is 10 minus 10 gives me the form 0 over 0, which is what I need for L'Hopital's rule. Okay, so L'Hopital's rule gives me a limit as x approaches 0 of f prime of x minus 20e to the x over 0.5 f prime of x. And remember, the derivative of the negative 10 there is just 0. Now plug in the zeros again, I get f prime of 0 minus 20e to the 0 over a 0.5 f prime of 0. The derivative at 0 is 4 minus 20 over half of 4, which is 2, which is negative 16 over 2, which is negative 8. And again, you'll note, solved all 4 parts of the problem, didn't touch a calculator at all. Now, thinking in terms of both problem 5 and problem 6, look at what's covered there. They have you take a derivative. They have you take a second derivative using implicit differentiation. They have you do an optimization problem looking for local max. They throw in there a Taylor polynomial. Though it's out of bounds, they managed to throw in an error bounding question. You don't need that one, but That one was there probably because it was part of an original problem and they didn't rewrite one. And then in problem 4, they move you from differential calculus to integral calculus. The first one is Riemann sums, coupled with a little bit of fundamental theorem of calculus. The second one there is working with a little bit of like a squeeze theorem in there, and recognizing that the integral is a limit and it's going to follow the squeeze theorem in that. The next part there is a straight up fundamental theorem of calculus problem, except for they're working with the second derivative in the first rather than the derivative in the original function. A L'Hopital's rule question, all like gearing toward the theory, but not making the calculations difficult. This is the kind of stuff that they're telling you should be looking for. I think that the going intuition is that that problem set is probably about right sized. It's probably close to right scope with the exception of the error bounding problem, but I think you've got something that's good and working here. So as you're working through other free response question sets, this is stuff to be looking at and thinking about. Make sure that you're seeing the balance of problem types and you're working at things that are not your strengths, and we'll get to there. All right, so we keep preparing.